Okay, this is the last unit in Unit 1, Physical Properties Matter. It's called Magnitude in Chemistry. So we're just going to talk about essentially the metric system and how the metric system works and why it is we use it in chemistry. Now, a little background here. You should have a pretty good grasp on this. You're juniors or seniors or sophomores, and you've seen the metric system before. So I'm going to go quick, but we are using this thing all semester. So if you struggle with it, please come in and see me. I'm not going to sit here and give like 19 different lectures based on just the metric system. So first of all, a little background. Created by the French in 1795. It's an international system. Everybody uses it in the scientific community. We're about the only country, developed country, that doesn't really use it full time. So awesome. And it has really two types of units. Fundamental units. Fundamental units deal with single measurements that describe a single phenomenon. So those are pretty simple. It's like time and distance and mass. So time would be seconds and distance maybe meters and mass would be like grams. And then we also have derived units. Derived units deal with two or more measurements that describe a single phenomenon. So we've just done something that has a derived unit, right? Density. Density is a derived unit. It's grams per milliliter. So there's two different measurements there. We put them together, we get a derived unit. There are many other derived units that we could talk about. Obviously, one you're probably very familiar with is miles per hour. However, that's not a metric unit. So kilometers per hour, right? That one's metric. And that's also derived. Okay? And then, like we said, grams per mil. Good, good. Those are all derived. Pounds per square inch. Okay? That's a derived unit, but again, it's not metric. Okay? So we could do something different. We could do newtons per square inch. Okay? There you go. So that's a unit of pressure, by the way. That's pressure. All right, so those are the two different types of metric units that we see. And there's some examples down there. All right, why do we use the metric system? Now, I know we've grown up with the English system, so we're very familiar with gallons. I totally get that. But the metric system is much easier than our standard system of measurement because units within the metric system are powers of 10. So here's an example here. If we wanted to convert 1,200 grams to kilograms, I gave you guys a green reference sheet to use in the past. You could look at that green reference sheet. I'm hoping you could figure it out. That would come to this number, 1.20 kilograms. Kilogram is a big thing, a gram is a little thing. So there's a lot of little things in one big thing. So in turn, my number for my big thing, my number for my kilogram should be tiny, and it is. Okay, 1.2 is smaller than 1,200. All right, so all we'd really have to do is move the decimal, but I'll show you the math that you can use to try to figure that out. On the other hand, if you wanted to convert like 40 ounces to pounds, okay, here's a little bit of math that it's like 2.5 pounds in order for that to happen. Now, I know that there's 16 ounces per pound, so that's not the worst one in the world. But if I were to ask you to like do an addition between 1 and 15/16 inches plus, let's see, 5/7 of an inch, I have no idea what that is. Okay, it would take me a long time to figure that out. I hate adding fractions. Adding decimals is super easy. Adding fractions, not so much. So that's one of the reasons, one of the many, many reasons why the metric system is preferred. Give me some basic units. Now, length, time, mass, meters, seconds, kilogram. You might say, well, why the kilogram? Why not the gram? Because the kilogram is a little bit more visible to us. Okay, a kilogram is like, like a large grapefruit. There's a kilogram. It's something we could actually hold in our hands. Grams are really tiny. A very, very small paperclip is about a gram, and it's just not the easiest to see. Meter is also the base unit for length because, again, it's easy to see. It's about the distance from the bottom of your foot to your hip. Okay? And time, and that's simple. Seconds, we all know what a second is. So you can see your green reference sheet that I've given you. If you've not gotten one of these, I will get you one. They're also posted on Edmodo, and those have all these types of basic units on them. Now, the metric system uses prefixes to tell the magnitude. Magnitude in chemistry, right? So if we want something really, really little, we use prefixes like micro and milli and centi. If we want something really, really big, we use a prefix like kilo or mega or giga or tera. Now, since we're getting these huge computers that can hold terabytes of information. Okay? So we can use a prefix really to tell the magnitude of something. So if we're talking like a nanometer, we know that's really, really, really small. Nanometer is like the radius of an atom. That's tiny stuff. Okay? Again, these metric prefixes are on your green reference handout for you to use if need be. Okay? So one of the most difficult things when it comes to this idea, when it comes to magnitude in chemistry and the metric system, is being able to convert your units. Okay, to be able to convert from units to units. So let me give you one example here. Let's say we have 15 grams of stuff. Okay, 15 grams. And I wanted to say, okay, well, how many milligrams is that? Now, if you're wise enough, if you understand your prefixes enough, you know that the milligram is a really, really tiny thing. So there should be a lot of milligrams in a gram. And if you know that milli means 1,000, which you should, because millennium is 1,000 years, so milli means 1,000, you might be able to say, okay, Cornick, I know I got to take my decimal place and swoop it over 3 times. And give me 1, 2, 3. So that's okay, comma there, so that equals 15,000 milligrams. That's what my answer is. And I would say, yes, you are correct. Good job. But maybe you don't know that. Maybe you don't know how to do that. So let me give you a little technique. You've got 15 grams, right? Let's make that look like a fraction. This is called the unit analysis method. Unit analysis. So if you look at your green sheet, I bet you can find something that says this. 10 to the third mg. It probably doesn't say mg. It probably says mm. But just roll with me here. Mg is fine. Over 1g. And again, it probably doesn't say g, it says m, 1m. Well, what it says on your sheet is mm is millimeter. Okay, so it says 10 to the third millimeters divided by 1 meter, or over 1 meter. Okay, that's universal. So you can say, it doesn't have to be meter, it can be grams, it could be liters, okay, it could be seconds, whatever. So 10 to the third milligrams in 1 gram is the same idea. So notice how I said that too, by the way. This thing right here, I said 10 to the third milligrams in 1 gram. Okay, so that little bar is like in. So when you see this little bar, it's like, oh, I should say the word in. There we go. Okay, all right, so I've got this set up correctly on my calculator. Then I know that I'm going to take 15 times 1,000, 10 to the third is 1,000, and that equals 15,000 milligrams. Yay! Okay, I got it. Okay, super. So that's wonderful. Now, a little bit more applicability here. Let's go back to what we were just learning. With density, let's say we've got like 1.3 grams per centimeter cubed. That was the density of the particular material that I was working with. All right, I'm going to rewrite that. I'm going to make that look like a fraction. So I'm going to say, okay, that's actually 1.3 grams per 1 centimeter cubed. So if I've got 1 centimeter cubed, it's going to have a mass of 1.3 grams. Great. And let's say I want to know, well, I want to know what that is, because I want to compare it to like some gases, right? So I want to know what that density is in grams per liter. So I got to do some converting. Okay, well, what do I know? You know what, from activity number 1, I think I recall that for every 1 centimeter cubed, there's 1 milliliter. Yep, that's correct. And notice how I put that. I put centimeters cubed on top. I wonder why I did that. I'll come back to it. I'm not done, because I've got milliliters now on the bottom, and I didn't want milliliters, I wanted liters. So I go to my green sheet, and I take a look, and I take a look, and I take a look, and I do find this. I find that there's 10 to the third milliliters. Again, it probably says mm, but that's okay. You now know that you can substitute over 1 liter. Now check out what happens. This is awesome. This is the unit analysis, right? Centimeters cubed goes away, milliliters goes away, milliliters goes away. Oh, I am left with grams and liters. There's grams and there's liters, and that's what I wanted right there. Woo-hoo. So I did it. Okay. Now, final answer. How do I get that? What do I have to do mathematically? Well, I have to. Let me erase those little circles. Okay. So now I have to take 1.3 times 1. I think you can do that. Times 1,000. Again, I think you can do that. And you have to divide that by what? Well, 1 times 1 times 1. So really, you have to divide it by nothing. So that's awesome. So 1.3 times 1,000. Can we do that? I think we can. That's 1,300 grams per liter. Awesome. You did a nice little conversion there. All right. Now let me get a little huge for you. Okay. Let's talk about like space, right? So this is a picture on the left side. This is a picture of what they call the ultra deep field. This is a picture taken by the Hubble telescope. If you can imagine this, these galaxies that you're seeing are 13 billion light years away. Now, a light year is a measurement of distance. Don't let that confuse you, because it's got year in it. It's a measurement of distance. Now, check this out. Check this out. Ready for this? So let's write that down. 13 billion light years. What if I was like, I don't know what a light year is. I want to know what that is in kilometers, because I kind of know what a kilometer is. There's like 1.5 kilometers in a mile, so I can figure that out. All right. So I might say, how many kilometers is that? Well, I need some type of tool for me to figure that out. First of all, let me write 1.3 billion in scientific notation. Right? 1.3 light years. There we go. Got to know scientific notation. I think we do. Okay. Now, the tool I'm going to use is this conversion factor that I'm going to build right here, my handy-dandy conversion factor. Now, your green sheet had a lot of conversion factors on it, Sometimes you might have to find a conversion factor that's not on that sheet. You ask me, I let you know what it is. So for the conversion factor of light years to kilometers, there are 9.46 times 10 to the 12th kilometers in 1 light year. Yeah, that's 9.46 trillion, by the way. That is huge. All right, now check it out. We can unit analyze this. Those go away. Okay, if I don't know how many kilometers are in that distance, that ultra deep field that I'm seeing right here, I can add those two numbers and let's see. I'm going to do the math in my head quickly. It's not going to be exactly right. You guys do the math at home and you tell me what it is, but it's something on the order of like 1 times 10 to the 21st kilometers. So go ahead and write that out, non-scientific notation. That would like take you a long time. Oh my God, do you know how huge that number is? That is just mind-bogglingly huge. And that's how far away these galaxies are. That's really, really cool. I think it's a pain in the butt when I got to drive to work. Okay? So what we just did right there is unit analysis using the metric system, using our converting techniques to find out a new unit. Okay? Now, are we ever going to have to find out like distances to off galaxies in or in chemistry class? Oh, probably not. But we will have to do things with molecules and atoms and some weird thing called a mole and stuff like that. And the unit analysis technique that I just showed you is going to be very useful. So let's keep that in the back of our minds for later on. All right, there we go.